Let's start by reviewing what we've learned thus far about probability. When we conduct a procedure, such as drawing a card from a deck, we can calculate the probability of an event such as drawing a heart using this formula. If we conduct the same procedure, drawing a card from a deck, we can calculate the probability of multiple events such as getting a red card or a heart using the addition rule. In this lecture, we will look at how to deal with the probability of 2 or more procedures such as drawing 2 cards from a deck, or rolling 3 dice, or flipping 4 coins. Notice how we have 2 equations for the multiplication rule. Which one we use is dependent on whether the first procedure has an effect on the second. If the outcome of the first procedure has no effect on the outcome of the second, we call the events independent. If my events are independent, then I use this formula, which says that the probability of event A occurring and then event B occurring is equal to the probability of event A times the probability of event B. For example, if I roll a pair of dice, what is the probability of getting a 2 and then a 6? Even though we are rolling the dice at the same time, we can treat them as 2 successive procedures. These procedures are independent since the number I roll on the first die does not affect the number I roll on the second die. Thus, the probability of getting a 2, then a 6 is equal to the probability of rolling a 2 times the probability of rolling a 6, which is 1 out of 36. Now this makes sense, since out of all the possible 36 outcomes, there's only one where you get 2 first and then a 6 second. Students often get confused that this is also an outcome. But remember that order matters. We are looking for 2 first and 6 second. However, this outcome states that you get a 6 first and then a 2. What is the probability of drawing an ace and then a king? In order for us to treat these events as independent, we must have replacement. Meaning, once we draw the first card, we must put that card back into the pile to ensure that we are picking from a deck of 52 cards for our second draw as well. Thus, the probability of drawing an ace and then a king with replacement is equal to the probability of drawing an ace times the probability of drawing a king. So if replacement is putting the first card back into the pile, what does without replacement mean? It means that you don't put the card back in before you make that second draw. This means that the outcome of my second draw is dependent on whatever card I draw first. What is the probability of getting a 6 of hearts and then a king without replacement? Since my events are dependent, I must use the second formula, which states that the probability of event A occurring, then event B occurring is equal to the probability of event A times the probability of event B, given that A has occurred. This vertical line here means given. Filling in the variables for this question, we get that the probability of drawing a 6 of hearts, then a king, is equal to the probability of drawing a 6 of hearts times the probability of getting a king, given that I've drawn a 6 of hearts. The probability of drawing a 6 of hearts is 1 out of 52. And the probability that I draw a king is 4 out of 51. Our denominator here is 51 since there is now 1 less card in our deck. Remember, without replacement. What if we ask a similar question? What is the probability that we will draw a king of hearts and then a king without replacement? Again, we will fill in the variables to read that the probability of drawing a king of hearts, then a king, is equal to the probability of drawing a king of hearts times the probability of drawing a king, given that I've drawn a king of hearts. The probability that I draw a king of hearts is 1 out of 52, and the probability that I draw a king, given that I've already drawn the king of hearts, is 3 out of 51. It's 3 since there's one less king, and it's 51 since there's one less card in the deck. An elephant, giraffe, and a shark are waiting to get on a boat before the Great Flood. There are only 2 spots left, and they will be filled randomly. Find the probability that the shark will be chosen, then the elephant. There are 2 procedures happening here. Choosing someone for spot 1, then choosing someone else for spot 2. Since there are multiple procedures, we know we have to use the multiplication rule. These events are dependent, since after one animal is picked, the total number of animals remaining will be reduced. In other words, this procedure is done without replacement. So, we should be using this formula. The probability that a shark will be chosen first is 1 out of 3, and the probability that the elephant will be chosen second, given that the shark had already been chosen, is 1 over 2.